All right, let's continue having our review on colligative properties. And I know we don't have Layla here today. We don't have Landon here today. So, maybe this will help people out if you choose to watch it. I want to go into looking out at Raoult's law in two cases. The easy case is that the vapor pressure of the solution is just equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Or not plus, that's solvent, and you multiply the solvent. So that's really easy, as long as you know how to get mole fraction. Now remember, what mole fraction is nothing more, let's say the mole fraction of A, I'm just going to label that A. That would be moles of A over total moles. And, luckily in these Raoult law problems, these vapor pressure lowering problems, we only have two things. So you don't have to, you're only going to have two numbers down there. Solute, solvent. Here, though, we just have to do it twice. Now, this is for the case of a volatile solute. So something like alcohol and water, or acetone and water, or acetone and alcohol. You name it. As long as they can both evaporate, then you're going to have to use that. So I'm going to look at a problem in the book here on page 549, if you want to follow along. If not, I'll write it on the board. I want to take a look at questions 49 and 51. And they're page 549, 49 and 51. So we can go through those. And I'll make this go a little better. So I'm just going to rewrite it. P for the solution, I'm going to say is equal to the mole fraction of the solvent times the pure vapor pressure of the solvent plus the mole fraction of the solute times the vapor pressure of the pure solute. Now, let me tell you something about this equation. Thank you so much. Oh my goodness. All right, I'll have to just drink it.
Wait,
oh.
You have
I drink black, strong coffee in the morning. And I guess it's not that bad, but... Oh, what was your question, Anna?
the mole fraction, and then
No,
there's the mole fraction, and then what do you do between that and the P of the solvent?
well, you're gonna multiply those terms, right? And you're gonna multiply and then add them together.
That be given?
Well, we'll look at the problem and then we'll work through it and see. I'll show you exactly how to approach it.
Is the P of the solvent
The vapor pressure of the pure solvent. Think of it this way. Let's just say I have a glass of water. And that glass of water is 100% H2O. And at room temperature, the vapor pressure of water is maybe about 20 millimeters of mercury. And then I say, well, I'm going to throw some acetone in there. Okay. And so many grams. So you have so many moles, grams to moles. You think, okay, well, pure acetone has its own vapor pressure. It's a lot higher at room temperature than water because it evaporates much more quickly. So this is like a weighted average between two quantities because you have the solvent again, think about what's happening at the surface here. You've got a solvent molecule, and maybe some solute molecules, and so you have this conglomeration of things leaving the surface of the liquid and contributing to the vapor pressure. Okay. Whereas up here, in this case, you only have solvent molecules that can evaporate. So this is like if I put sugar in water or something. But anyway, let's take a look at this. And I want to mention, this is an ideal equation. This is for the case of ideal solutions. Now, what that means is that we are assuming that there's no interaction between molecules in our our mixture here. So if I put, say, ethanol in water, ethyl alcohol in water, according to this, we're going to just pretend that the water and the ethyl alcohol just are ignoring each other. They're just doing their thing. But in real life, you have to make modifications of this because you can have interactions between molecules. But that, when you take physical chemistry in college, then you'll learn that stuff. Right now, we're going to look at ideal solutions. So let's take a look at question number 49. It says pentane and hexane form an ideal solution. At 25 degrees C, the vapor pressure of pentane and hexane are 511 and 150 torr respectively. I think we actually went through this one, but it doesn't hurt to look at it again. So let's take a look. And let's try to think about what we're doing. We have a beaker, let's say, and we have some pentane in here, C5H12, and we've got some hexane, C6H14, and we mix them up. And this says, this also has density in there, which we're going to need. So let's write down some things that we know. First of all, we know the vapor pressure of pure, let's call this pentane. So I always suggest writing down what you know, what you're given, and the vapor pressure of pure hexane. And I think that pentane was 511 millimeters, was it? I think, is that what it said? 511 and hexane has 150 torr is its vapor pressure of pure hexane. Now look, we're mixing some hexane and we're mixing some pentane. So the vapor pressure of the resulting solution is going to be some weighted average of these two. And weighted average, of course, means that you have to account for, well, in this case, the weighting factor is the mole fraction. So let's take a look here. And it says, well, we're mixing 25 milliliters of pentane. So milliliters doesn't do us any good. 25 milliliters C5H12, and we're mixing that with 45 milliliters of hexane. Hexane is a very different thing. So we know that we've got more hexane than we do pentane, but we have milliliters here. So if you have milliliters and you want to get to grams so we can get to moles, we need to use the density. So the density, we're told how many grams per milliliter. And for pentane, it's 0.63 grams per milliliter. And for hexane, it's 0.66 grams per milliliter. And of course, if ever you had water, water is always going to be 1 gram per milliliter for our purposes. So the next step is, before we can go and get mole fractions and stuff, is we have to get grams of these things, and then we have to get moles of these things. Well, that's easy enough. So if I multiply 25 milliliters by the density, the milliliters cancel. So 25 times 0.63 is 15.75 grams of C5H12. And in this case, we've got 45 times 0.66. And I get 29.7 grams of C6H14. And now we want to get moles. Now remember how to get moles? Add these guys up. So we've got 5 times 12 for the carbon, that's 60, plus 12 is 72, 72 grams is 1 mole, so 15.75 divided by 72, we have 0.219 moles of pentane. And down here, getting a little sloppy. I was watching this video, And it said one of the characteristics of high IQ people is that they are incredibly disorganized. So I think I'm just incredibly disorganized and has very little to do with IQ. But anyway, let's go ahead down here. And we're also easily distracted. That's another characterization. How you doing, Carolyn? Good. That's bad. Okay, so C6H14. We've got 72 grams of the carbon for the 6 carbons, 14, 86 grams in 1 mole. So let's get the number of moles. 29.7 divided by 86. And that's 0.345 moles of hexane, C6H14. So now we're all set to go to use Raoult's law. The solvent is typically the one in larger quantity. As I said before, though, these things are totally miscible, which means they are totally soluble in each other in all proportions, so it doesn't really matter which one you call which. But let's stick with convention. The one in greater quantity is going to be our solvent. So the mole fraction, that's going to be 0.345 over 0.345 plus 0.219. So that would be the mole fraction of that. And let's multiply it by 150 torr. And the mole fraction of the solute, which in this case is the pentane, is going to be 0.219 over 0.345 plus 0.219 times 511 torr. So if you just, before you do any math, you take a look, you say, okay, I'm going to have a contribution from this and a contribution from this, so my answer has to be somewhere between these two numbers. If you're doing a Raoult's law problem like this and you come out with a number that's lower than the lowest pressure or higher than the highest, you've done something wrong. All right, let's chug and plug here. 0.345 divided by 0.345 plus 0.219. And that's, get rid of this here. Make it look a little neater. That's going to be 0.611 times 612 times 150 plus 0.388 times 511. So let's go ahead and do that. You're going to have 0.612 times 150. So that is 91.8 torr. And we're going to add that to 0.388 times 511. And that's 198.2 torr. So we add those two together. And I get 290.1 torr. Equal the answer. See how those go? These are a little trickier than freezing point, boiling point, osmotic pressure, because you have to think about things. You have to get these densities and maybe use those, and then you have to get mole fraction. And so conceptually, it's a little tricky. Not too bad though. All right, let's take a look at question 51. 51 is another one. Before I go on, though, how about you guys from yesterday? You good with like boiling point, freezing point, and osmotic pressure? Great. Next week we're going to start, and I'll make videos so you guys can watch them when you're in North Carolina, or is it South Carolina? South Carolina. You can watch them. We're going to be talking about things called phase diagrams and some other Clausius-Clapeyron equation. Good stuff. Okay, so number 51 says, what is the composition? What is the composition of a methanol propanol solution that has a vapor pressure of 174 torr at 40 degrees C? The vapor pressures of methanol and propanol are 303 and 44.6 torr respectively. Assume the solution is ideal. This is kind of reverse engineering the problem we just did. So what they want to know, they want you to tell them, hey, what's the mole fraction of each of these things? What's the mole fraction of the propanol and the methanol, whatever we have here? You got to think about your algebra skills here, and this is an exciting problem. Okay, so remember, if I have two things, what do their mole fractions have to add to? Cricket. If I have a third of a pizza and Mackenzie has 2/3 of a pizza, they add to 1. Yeah. So XA plus chi A plus chi B has to equal to 1, right? So we are told that the vapor pressure of this mixture is 174 torr. Okay? This problem's so good it gives me goosebumps. So let's call this X for the which one do we have here? No. Well, yeah, you can add two fractions and not get one. But if I have half a pizza and you have a half a pizza, we're splitting it. We have one pizza. Right? So if I've got a mixture of two things, and part of it is X, the other part has to be 1 minus X. Yeah. So that's what we're doing. So let's just call that one chi, for mole fraction. And we'll just, it doesn't matter which we use here because we don't know which is which is the solvent and which is the solute. So pure methanol has 303 torr. I'm going to call that 1 minus chi, and then that's going to be 44.6 torr. Okay? So this, I called the 303, that was the methanol, CH3OH, and this over here is going to be the propanol, CH3, CH2, CH2OH. I'm going to put this on pause, and I'm going to see if you can do the algebra and solve for those two values. I think you can do it. I'm going to leave the units off just because it makes life easy. So 174 is equal to 303 times chi plus, let's distribute this, 44.6 minus 44.6. Take the 44, get our like terms, minus 44.6. That gets rid of that. And what else? Yep, so what do you got? 303 minus 44.6. That's an X or chi. So what'd you get on this side? 258 X chi. I'm going to say X. And what'd you get on this side? 0.4? How about that? 129.4. Divide through. Boom. 258.4. 258.4. So give me that number. 0.5.
Yeah.
0.50.
01.
0.501. All right, that's this number. So we've got 0.501 for the methanol and basically 499 for the other one? Yeah. So the mole fraction from chi for the methanol, CH3OH, is 0.501, and for the other one there, for the propanol, CH3, let's forget it, I'm not going to write out that. It's 0.49. Brilliant. Good problem. You see how we did it? That's okay. I don't get in your way. That is really a good problem.